Hello, my name is Marcel Hübener. I'm a quality engineer here at IDS, and I will talk today about the cleanliness of our cameras and under the title When Clean is Not Enough. The agenda is for today: what are the critical applications and where is no defect allowed? Also, what does a sensor see? What visible dirt or defect? What are the typical errors? How IDS can find the error, the IDS defect detection? What's possible and worth the money? What's technical possible, but at what cost? And, for your benefit, the solution proposal, the way to your clean camera. Let's start with a little example. This year, the NASA landed the Mars rover Perseverance successfully on the Mars surface without any damages. After years of preparation and months of time in space, the rover is now able to send pictures back to Earth, and after days a crew member of the NASA spotted unidentified life on the Mars surface, a structure or creatures. They spent several hours or weeks or months to analyze the structure or thing. They don't find any explanation or fact. After some more hours of analysis, they find out it's only dirt in the optical system. Over the next years, in every picture the camera takes, these defects will be contained as long as the rover travels over the surface of planet Mars. To prevent our customers from such effects, it is important to understand what cleanliness of a camera means and what is needed to provide a high quality. At first, we want to explain what the critical applications are. In applications which provide only a small difference between different gray values, a defect may have big effects. Images with a very uniform contrast gradient are also critical. A good example is a picture of a flower field compared with a white wall. Applications which contain such a characteristic are mostly transmitted light methods, like for the glass inspection. For the glass inspection, the algorithm only detects if a defect is present or not. Often it is not possible for the system to recognize where this error comes from. Is this defect caused by the sample or by the camera? In the picture, it is clearly visible a particle of dirt in the camera cannot be distinguished from a spot in the sample. With this misinformation, the system produces mistakenly rejected goods. Applications where the complete image is needed for an analysis, as it is in the particle analysis or the glass inspection, are also critical. Here the software or employee detects a particle or structure which isn't there by mistake. So there will be incorrect information created and you get different results between machine A with a good or clean image and machine B with a dirty image. This already shows that the impact of a defect or dirt in the optical path is depending on the application and the target or object the camera is looking on. So dirt or defect hasn't got such big impact on a QR code scanner than to an analysis of a glass sample. Another reason why you can or cannot see a spot in the image is often the illumination. Parallel light is the critical lighting par excellence among its many advantages. So what is parallel light? For parallel light, all light rays move nearly parallel to each other. So it is often called collimated light. To direct diffuse or not orientated light to parallel light, a collimator is needed. Inside a collimator, the light will be focused to infinity. So why and for which application do you need parallel light? Especially to visualize flat defects or dents on surfaces. Furthermore, it's very suitable to make defects visible in transparent materials. So, how does it work? To explain how parallel light works, let's make an example. We take a perfectly flat surface and send perfectly parallel rays of light at a 90-degree angle to the surface. Due to the law of reflection, the light rays are reflected back in the same direction from which they came. So every light ray will be caught by the lens and hit a sensor of the camera. As a result, the camera will generate a bright image with no visible defects. Is there any dent or defect on the surface, the parallel light rays will be reflected to several directions because of the shape and the angle of the defects or dents in the surface. Thus, the optics or the camera receives no information from these spots, which in turn means the spots are displayed as a dark or black spot in the image. The opposite of a parallel light is the usage of a diffuse light. Diffuse light will be used when you want to inspect reflective or shiny metallic surfaces. If the surface is dented or curved, the task becomes more difficult for normal light sources. Diffuse light has no three-dimensional order. With a diffuser you can create diffuse light. Like in the picture you see, it's a diffusing lens. It is important to say that this diffuser reduces the intensity of light. If the diffuse lighting is good, the reflections are significantly reduced, dents or curves are nearly invisible, because at any time a light ray or of an area of the inspected surface object will find a way back to the lens or sensor. All defects will be made invisible, as you can see here in the image. Based on this initial information, we can make a small summary of which circumstances lead to a visible defect and its consequences. So, what is a sensor able to see? A camera does not work like the human eye. The eye of a human or an animal can adjust to many different influences at the same time. A camera, however, is dependent on the two basic pillars of optics. First, the camera only sees what the lens of the camera allows it to see. Second, the camera only sees what the exposure is capable of illuminating. As we have already seen with illumination, diffuse lighting can obscure many things. When combined with an endocentric lens, virtually all defects in the optical path are invisible to the camera. This accords with the most applications of our customers. An application with parallel light and a telecentric lens, however, makes every defect in the optical path visible. If the image is also averaged over several images, the defects become even more obvious. As you can see in the image on the left, several defects with collimated light are visible. On the right side, this camera is looking at an object with the same defects. Here the defects look almost the same as the defects on the surface. If the surface had no defects, the object could be evaluated as not okay because of the spots in the camera. Assuming that a defect is visible in the following, let's take a look at some typical defects or dirt and how they differ. Dirt on the sensor cover glass. Very often there is dirt or residues from the manufacturing process on the sensor itself. Mostly loose dirt, which will be cleaned in our standard production process. This dirt can often be removed with cleaned and dried compressed air or isopropyl alcohol. The loose dirt is visible in the camera image as a dark or black spot. If the spot is visible or not depends on the light source, shape of the dirt and the used lens. Since the defect is very close to the active area, the spot in the image has hard edges. On the short distance between dirt and the active area, the deflective effects are very minimal. Scratches in the sensor cover glass. Very often our employees find slight scratches in the sensor cover glass. These are often caused by incorrect handling. The wrong cleaning tools or cleaning methods can also cause this problem. Scratches cannot be removed or polished. In the sensor image, scratches are displayed as many small points or as a dark line. The form and how it will be displayed in the image of a camera depends on the illumination and the used lens. Defects in the coating of a filter can vary in the way they are visualized. The most defects on a filter are coating defects. In the camera image, a coating defect looks similar like dirt on the sensor cover glass, but defects in or on the filter have rings around a dark area in the middle. Those rings are caused by deflection, which will lead to destructive or constructive interference. Glass inclusions or scratches are also a problem in the filter. The filters of our cameras are very sensitive, so they can also be scratched very easily. The scratches look nearly the same as a coating defect, but they are very difficult to detect. To understand where these errors came from, let's take a look at our filter glass and how they are specified. There are several ways to specify a filter glass or an optical surface. The old way is with the specification of the American military from 1997. The inspection will be done before or under a specified lighting source and with a laboratory standard to compare defects. This test will be preceded by a trained employee of the filter supplier. The filter will be specified with two parameters. At first parameter scratches and the second parameter point-shaped defects. This will lead to SD value. Possible values range from 8050 to 2010. Values beneath 2010 are not reachable with a coated surface. As an example, let's take a 16mm filter glass with a specification of SD 4020. Let's start with the scratches. The darkest scratch or the scratch with the highest contrast will be compared to sample. With this sample, the employee can decide if the filter is matching the requirement of a maximum scratch level of 40. The darkest scratch must not be darker than 40. The length of the scratch is not evaluated in this step. The point-shaped defects are also classified with a reference value. Point-shaped defects with a defect value of 20 shall not be larger than 0.2 mm or 200 micrometer. The maximum allowed scratch length will be specified as followed. The sum of all scratches with a maximum scratch level of 40 shall not be bigger than 1/4 of the diameter. In our example, the sum of all scratches must be smaller than 4 mm. The total number of maximum sized point-shaped defects shall not be larger than the diameter of the used filter divided by a standard diameter of 20 mm. In our case, only 0.8 defects are allowed. And finally, the sum of all diameters of point-shaped defects shall not be bigger than the double of the maximum number of defects multiplied with the defect size in millimeter. For our example, we get a sum of diameter of 0.32 mm or 320 micrometers. As you can see, the specification and its evaluation is very economic and fast, but not very precise. It's only a visual inspection without image processing. It depends on the knowledge and experience of the employee, so all in all, this specification can be a little bit rough. Another way for the specification is the ISO standard 10110. It is the standard for the creation of technical drawings of optical surface and their toleration. It is much more precise and it's based on physical values and frequencies. But the evaluation or testing needs much more time and the needed equipment is very expensive. A microscope with very high magnification is needed. Because of the magnification, the field of view is reduced significantly. Following this, a sample with a certain size needs several measurements, taking an amount of time. The standard doesn't distinguish between scratches and point-shaped defects. The defects will be classified over quantity, size and the defect area in square millimeters. But there can be much more conditions tested than the surface defects. So, since 2 years, IDS is in close contact with our filter supplier to optimize the quality of our filter glasses constantly. Here we focus on our customers' requirements and how a camera with high quality standards can be produced economically. So, we changed the filter specification for our filters. Because we found out by several tests that the mill specification, which the most filter manufacturers are using, doesn't fit to the IDS way and what our customers are searching for. Even if we are in steady contact with our filter supplier to optimize our filters and get a nearly perfect filter, we analyze every sensor and filter in our cameras by special test methods to find possible defects. Now let's take a look at how IDS can detect defects and dirt in our production process. With the IDS passive sensor control tool, we are able to find defects. It's called PaCo. An IDS camera is looking from above through a special lens and with a special illumination onto a sensor. Because of the special and ideal conditions, we are able to detect defects and dirt on or in the sensor cover glass. Every CMOS sensor has roughly the same design. The housing and the active area will be covered with the sensor cover glass. This cover glass protects the microlens array and the active area from external impacts. In and on this glass there can be defects, inclusions or dirt. Beneath the cover glass there is the microlens array which collect light for the underlying pixels. Under the microlens array the color filter or biopattern is located, which is printed directly onto the pixels. Let's start with the operating concept. For checking a sensor, the PaCo station will focus after the start of the test to the top surface of the sensor to detect any dirt. After PaCo receives a well-focused picture, this picture will be saved. After this step, PaCo focuses to a plane in the sensor cover glass to take there an image as well. At least PaCo take a picture of the bottom side of the cover glass. After all pictures are taken, PaCo will summarize the pictures to show the employee an image with a result. This result shows where defects in the sensors are located. After the sensor is checked and evaluated as OK, the sensor board with the soldered sensor can be mounted on the camera front end or lens holder. This assembly group looks nearly the same in every camera. On the cover glass of the sensor a sealing which is pushed against the filter glass is located. The filter glass and the sealing protect the room between the sensor and filter glass from any dirt. With the same PaCo process, we look inside the camera after assembling the front end. Like in the sensor clean, we check at first if there is any dirt on the filter. After that, the filter is checking by taking pictures. PaCo summarizes these pictures and shows the employee defects or an OK result. After that, PaCo will focus to the sensor surface again to check if there was any damage caused during the assembly. If this check is also OK, the camera can be moved on to the next production step. In the last production step, our cameras are 100% final checked. In this final test, the cleanliness of our camera will be inspected by trained employees. Through the combination of the human eye and PaCo, we receive the best results. By using orientated light emitted by a LED similar to parallel light, we are able to visualize defects in the final test. If no dirt or defect can be found, the camera is ready for shipment. As the previous presentation has made clear, cleanliness is not always the same and depends on various influences and requirements. We will now take a look at what is particularly possible and under what economic influences using an example. We have seen many defects over time and have identified that a filter plays a major role. Since 2 years, we are in close contact with our filter supplier to improve the filter glasses step by step. For this purpose, we have sent in filters with defects and had them examined by the filter experts of our supplier. One challenge was to see the same faults, and it turned out that the defects are in the micrometer range and reach from 100 micrometers to 32 micrometers and even further down to 3 micrometers. Mostly these defects caused by the surface coating of the filters. Scans of the surface show that peaks and valleys cause the spots in the image. The reflections and diffractions at the edges of the defects then cause interference with the light and thus lead to characteristics and appearance of the defects in the live image. We exchanged defect image and filters with our supplier. Our supplier was able to determine that there were significantly more defects visible under the microscope than we could see in our live image. Especially look here on the image on the left side. These are the live image of the sensor, and here the spots 4 and 7, which you can see on the right side under the microscope, are not present. The microscope image shows that the spot 3 and 5 look very different from the rest of the defects. This was dirt on the filter glass. The defects 2 and 6 are surface defects that are clearly visible in the image. The defects 4 and 7 are also surface defects, but these defects are quite small in contrast to the other defects. Over the number of filters we have examined, this has resulted in the following impression. Most defects up to approximately 7 micrometer plus minus several micrometers are not visible with the test setup we used. Larger than 7 micrometers, these defects slowly become visible until they were very clear above a certain size. From this investigation, it became clear that the distribution of defects is around a mean value and that there are aberrations in both directions, as you can see in the image. To minimize the frequency and size, our supplier changed the coating machine. Here, tests have shown that we are able to achieve better results at an economically justifiable additional cost. The detection and selection of filters takes time and therefore costs money. For this reason, the amount of effort required must be carefully considered. Using only filters with defects of a maximum size of 5 micrometer is unrealistic and expensive, whereas most customers do not need this quality. We try to find the right camera for all customers, and 90% of the customers are satisfied with the standard version. For all others, there are available options. So it is technically possible to detect filters and sensors with defects smaller than 10 micrometers. However, this requires special equipment like special microscopes, special illumination, special environmental conditions, so increased clean room requirements, and the most expensive part is the increased effort. Furthermore, the failure rate on the part of IDS and their supplier for these special cameras must also be taken into account. Of course, this also increases the cost of materials. At some point, of course, the critical cost point is exceeded. Here, material costs, effort, machine hours and the special equipment add up to a point where the camera price reflects the effort, but from the customer's point of view, it is somehow overpriced and no longer economical. Also, these special requirements ties up personnel and reduces the overall productivity of production. However, there are more attractively priced options in this concept. So, in summary, it can be said that a detailed requirement analysis based on a few questions can clarify a lot in the run-up to a project in order to avoid surprises or problems later on. A clear, detailed specification is half the job. What kind of application does the customer have? A transmitted light application or a glass inspection? What kind of lighting does the client use? A parallel, diffuse light, orientated light? What kind of lens is being used? What camera is the client using and what settings are used for the camera? The information in how the customer checks the cleanliness of a camera is also of great value. An IDS camera is always a good baseline for argumentation about cleanliness. A customer should check for camera cleanliness in its application with a standard camera. Evaluate if this cleanliness is okay or affects the result of the application. If the customer finds defects, where did they occur? In the incoming goods inspection or in the application itself? Also, does the incoming goods inspection correspond to the application? Are they cosmetic defects or do they interfere the function? So, as these defects are usually caused by the filter defects, the use of an IDS camera variant without filter may be a solution for the customer. Please note that any filter properties, such as the IR filter, must then be realized in other parts of the optical path. Using a camera without a filter does not result in any disadvantages. If the no filter option is not clean enough or is not an option for you, then the next step is to switch to the microscopy clean option. Where in the standard cleanliness some errors are still allowed, in the MIG option, defects or errors should be ruled out. It is important to note, however, that not all sensors can be offered with a MIG option and not all models are suitable here. For more information, please contact here our sales and our product management team. And if both options are not enough, please contact our sales team. Then we will discuss with you whether a customized camera or process can be a solution. In this case, tests will be carried out to see if we can meet your requirements or if another solution is possible. In all cases, our machine vision consulting, sales, product management team and the quality department will be happy to assist you. I thank you for your attention. And if you have any questions left, I'm now available for a discussion.